Okay, so we had just been talking about the solution to this problem we looked at, where we kind of thought about how the way the differential equation was written is it's a little bit like an undamped spring, where we have a sudden forcing term at t equals 2 pi, where we just push that spring once and then let it go back to its thing. And when we went ahead and solved the Laplace transform problem, what happened was that even though we had introduced a delta function at t equal to 2 pi, what came out of the solution was a step function that turns on at t equals 2 pi. So after we crossed that point where we made that forcing term, the effect of it always appears. It doesn't only appear at t equals 2 pi, it carries on through the solution even after that. And so I said we were just going to think about what delta did here. So the delta in the forcing term only happens at t equal 2 pi. The rest of the time it's 0. But the solution carries the effects of this for all t bigger than 2 pi. And so what I'd say is, first, let's just think about whether that makes physical sense. If you have this undamped spring, you know it's going to oscillate forever unless you bother it. If you do bother it, there's no reason like you shoving the spring and changing its behavior would suddenly disappear after you were done shoving it. You've already impacted the system, and so there's no reason for that to go away unless you could somehow take back your actions. Even if the forcing term is temporary, we expect its effects to persist. In the absence of like damping that makes that sort of die out over time. Now let's think about whether that makes mathematical sense. So this is our forcing term. And what's important to know is that solving ODEs is fancy integration. We may have gotten away from that intuition these last few sections when we're working with Laplace transforms, but every way that you learned how to solve differential equations up to this point involved manipulating them and using some neat integration to get an answer. And since delta of, the integral of delta is 1, sort of what's happening is as you run over your integrals, they would be 0 up until 2 pi, and then they would jump up to 1 after you've crossed 2 pi. Think about like area under the curve. There's no area under curve here or here. All of that area fits in at 2 pi. So we're kind of like hanging around at 0, and then at 2 pi, we jump up to 1 right there. And this is exactly what the step function looks like. We learned it's something that's 0 up until you hit a point, and then it jumps up to 1 afterwards. And this has all probably seemed a little bit circular. Like we found this solution, so I've explained why the solution makes sense, but sort of why do we do that? And the reason I wanted to really emphasize this point is because I want you to realize that anytime you have delta in a differential equation problem, you need to have a step function come out of your solution. And I'm going to underline that a couple different times because it's just one of these things that you can use to always check whether or not you made a mistake. If you solve a problem where you had delta in your differential equation and you find that you don't have the step function, then something went wrong because you have no way of describing that the delta function didn't do anything until the moment it appeared, and then suddenly there's a change. So just whenever you're solving these problems, use that as a little hint to make sure that you're doing things correctly. These problems are long and it's easy to get lost and make mistakes. So the more ways you have to check your work, the better off you'll be. In the next video, we'll go ahead and talk about those periodic functions.